Okay, so yeah, so two of the books are already there in the VLE, so you can go through them when you have time. And right, so let's start to talk about automata theory. Okay. So, what we discuss in automata theory basically is about computations. So, automata theory in a nutshell is about computations. So, what is a computation? Well, computation is a task or an activity that can be performed by a calculator or a computer or some sort of machine. Okay, so what we discuss in this subject is how we can mathematically model a computer or some kind of a machine which performs a computation. Okay, so we'll be studying the theory about it, which is to say we'll be studying the definitions, the properties of a machine, what problems that can be solved by a machine, its limitations, etc. Okay. Right. So that is what we say in this first slide, that we are talking about computations and we're trying to model it. We're trying to model a machine which carries out a computation. Right. So before we move into talking about the crucial areas, we first start with the basics. So the basics of this subject start with something called a symbol. Okay, so the basic element, the basic concept behind automata theory is a symbol. So a symbol could be, let's say a symbol could be something like A or B or 0, 1, anything. Okay, any character could be a symbol. Okay, so a symbol could be any character, either A or B, 0, 1, anything. Okay, then after that, what we can do is we can get a collection of symbols or a set of symbols together to create something called an alphabet. Okay, then a set of symbols becomes an alphabet, a set of symbols. So how we denote an alphabet in automata theory is usually using sigma. So we can say, for an example, sigma is equal to AB, the set which includes A and B, which means A, B are symbols and they together create the alphabet. Okay, so an alphabet could include any number of symbols, okay, which means sigma could be AB, or sigma could be 0, 1, or sigma could be 0, 1, 2, 0, 1, 2, up until 9, any number of symbols, but it has to be finite. Okay, a main thing here is that an alphabet should be finite. At the same time, it cannot be empty. It has to be non-empty. Okay, so a finite non-empty set of symbols create an alphabet. හරිද? ඊට පස්සේ after an alphabet we talk about something called a string. A string. So what is a string? A string is a sequence of symbols formed over an alphabet. හරිද? ඒ කියන්නේ let's take for an example our alphabet sigma is equal to AB. Okay, so what are the characters or what are the sequences of symbols that we can form over this alphabet? We can take A. A is a sequence of symbols that we can form over this alphabet. A taniyama. Then we can take B, or we can take AA, or we can take AB. You get it? Or we can take BB, anything. Sequences of symbols that we can define or generate from a particular alphabet. This is called a string. Okay, so a string is always defined over an alphabet. That is important. If there's no alphabet, there will not be a string which we can generate over that particular alphabet. Okay, so symbols will get collected together to create an alphabet, and then using an alphabet we can create a string which is formed over that particular sigma or the alphabet. So you see that this A, the first string that we formed over the alphabet, is of length, this is length 1. This is also 1. Metana dekai. And then there will be strings of length 3, length 4. So you understand that strings could be formed of different lengths. There could be strings formed on an alphabet of different lengths. Okay, so now we get a question. How many strings of a particular length can we form over an alphabet? You get the question. How many strings of a particular length can we form over an alphabet? For example, how many strings of length 1 can we form over sigma? How many strings of length 2 can we form over sigma? How many strings of length 3 can we form over sigma? How many strings of length n can we form over sigma? This is a question that we might get. Okay, so now let's see how we can answer this. Okay, now let's first see if our alphabet sigma is AB. Okay, then let's understand how many strings of length 1 we can form over sigma. So what are the strings of length 1 we can form? It's either A or B. So there are only 2 answers. Okay, how many strings of length 2 can we form over this alphabet? Well, it is either AA or AB or BA or BB. Yeah, this is the set of strings that we can form of length 2, dekai. So how many symbols are there? There are 4 symbols here. We'll get another set of answers. So before we move on, I'll highlight this. What is the length of our alphabet? Length of sigma. The alphabet length dekai, because there are only 2 characters. We symbolize this by saying modulus sigma, which is to say the absolute value of sigma is 2. Okay, length of the alphabet is 2. If we come here and symbolize this using the length of our alphabet, this is going to be 2 to the power of 1. Then if you do the same here, this is going to be 2 to the power of 2. So 2 is the length of our alphabet. Sigma ge length එක තමයි 2 කියන්නේ. And the power එක 2 to the power of 1. The power is the length of the string that we want. power එකේ string එකේ length එක. Yeah, so it's the same here, sigma to the power of 2. 2 is the length of the string that we wanted. Okay, so then similarly you can say, by looking at the pattern, you can say that by any chance we come across the next question where we check the number of strings that we can form of strings of length 3, then you can say that the answer that we will get is 2 to the power of 3, which is 8. So there will be 8 answers, 8 strings that we can form of length 3. Over which alphabet? Over this particular alphabet. හරිද? ඔහොම ගිහිල්ලා අපි n වලට આવොතින් n දිග strings කීයක් හදන්න පුළුවන්ද කියලා આવොතින්, how do we do it? Now, how many blanks will we have? We will have blanks like this. How many blanks? We will have n blanks, n spaces that we need to fill. Okay, and each blank can be filled with either A or B. දැන් මේකට මට දාන්න පුළුවන් A හරි B හරි. මෙතනත් A or B. මෙතනත් A or B. ඔහොම I have n number of blanks. Okay, now this is the string, which means I have 2 options to fill this blank, 2 options to fill this blank, 2 options to fill this blank, so on and so forth. I have 2 repeated n times, which means I have 2 to the power of n options to create strings of length n. Alphabetic length to the power of n options to create strings of length n. Okay, so just keep this in mind, because in a little bit of time we'll be discussing further about this case. So we can get the number of strings that we can create over an alphabet, strings of a particular length, by taking the length of the alphabet and taking the power of the length of the string that we want to create. Okay, right. So before we move on, what did we discuss so far? We talked about a symbol, which is the basic building block in automata theory. Symbols got together, a set of symbols created an alphabet. Then a sequence of symbols that we can form over an alphabet, we call that a string. And then we moved on into talk about lengths of strings, lengths of strings. And then we spoke about how many strings of a particular length can we form over a given alphabet. That's what we talked about so far. So you see here, we came across a few words. We came across the word set over here. We came across the word sequence over here. So with these 2 words, we come into discuss certain mathematical basics, which you already know, mathematical stuff. Let's call that preliminaries. You already know these. So let's start with set. So what is a set? We know what a set is. A set is a collection of symbols. For example, let's say 0, 1, 2, 3. So it's a collection of symbols. And if this set is set S, and since 1 is an element in the set, how do we symbolize that? We say 1 is an element of set S. Then we talk about a sequence. We said a string is a sequence of symbols formed over an alphabet. So what is a sequence? A sequence is an ordered collection of symbols. Okay, it's a collection of symbols which is ordered. For example, say you have 2 strings. You have string 1, string 2. Okay, we can say that these 2 strings formed over a sigma, a particular alphabet, are equal, these two are the same, if their letters are the same and the order of the letters are the same. Or දෙකම සමානයි නම් we say this string is equal to this string. For example, අපි කියමු S1 කියන්නේ AAA, S2 is AAA. Now the letters of these two strings are equal, the same, plus the order of the strings is also the same, so we say S1 is equal to S2. Then අපි කියමු වෙන case එකකදී S3ABA, S4AAB. Now the letters are the same, but the order is not the same. Order is different. The order in which these are placed is different. Because of that, these two are not, we can't say that these two are the same. These two are different. Next, we talk about a tuple. A tuple is a finite sequence of objects, or we can say that this is a finite ordered list. Okay, so if we have, let's say, for example, two tuple. Okay, this means that there are two elements in this sequence. Okay, there are two elements in this sequence of elements. And then if it is a three tuple, we say that this is a sequence of three elements. If it is four tuple, then we say this is a sequence of four elements. Likewise, if in general we say k tuple, this means this is a sequence of k number of elements. It's a finite ordered list. Okay. Finally, the last one, again, you know this, Cartesian product. Cartesian product. So let's say A cross B. Then A is equal to 1, 2. And if B is equal to XY, then we can say the Cartesian product between these two is equal to, 1x, 1y, 2x, 2y. So in general, we can denote the Cartesian product by saying that it is a combination of two elements, A, B, where A should be an element of A and B should be an element of capital B. Okay, so these were a few basics with respect to mathematics that we needed to look at. So now, going back to our first discussion where we started off with the basic symbol, alphabet, strings. Okay, so now in this triangle, you see we have symbol, which we spoke about. We have alphabet, we spoke about that as well. Strings, we did that. And finally, we have language. Strings join when a language will. So after this, the next arrow we have is the language. We didn't speak about language. We went on to discussing about mathematical stuff. Now we come to talk about a language. Okay, the next part in the flow chart is a language. So we have a symbol, we have an alphabet, we have a string, and now we have the language. Okay, so we know that a string is a collection of symbols, sequence of symbols. Okay, now let's take an example. Let's take English language for an example. English language. Okay, so we know that English language has letters and words. Yeah, so basically letters are the people who form words. So it's basically a collection of words. We can say that English language is a collection of words because words are made out of letters. හරිද? දැන් අපිට කියන්න පුළුවන් දැන් අපි දන්න ටිකෙන් අපිට කියන්න පුළුවන් letters කියලා කියන්නේ letters are similar to symbols because they are characters and words are identical to strings. ඒක තේරෙනව නේද? දැන් මේකේ තියෙනවා symbols A B C D up to Z and these people get together and form words. Yeah, so we can say in simple English that this language, English language, is a collection of words, which is to say it is a collection of strings. Yeah. So this is the definition we use in automata theory to define a language. Okay. So in automata theory, we define a language by saying that it's a collection of strings. So a language will have a set of strings that are being formed over a particular alphabet. So let's take an example. Sigma is equal to AB. Our alphabet is AB. The alphabet has two symbols. And then let's define a few set of languages on this alphabet. Let's say language L1 kila kiyanne set of all strings of length 2 formed over sigma. හරිද? Set of all strings of length 2 formed over sigma. එතන මේකට මොනවද එන්නේ? එකට යනවා අපි කලින් කතා කරපු set එක. EB. Okay, so you see this is a finite set. So this is a finite language, we say. It's a finite language. Okay. Then let's take another language. Let's define another language on the same alphabet. This is the set of all strings of length 3 formed over sigma. Okay. Then what do we get here? We get AAA, AAB, ABA, ABB, BAA, BAB, BBA, BBB. Okay, this is the set of all strings of length 3 that are formed on sigma, which is our alphabet. අපි තව එකක් define කරමු L3. I'll say that L3 is the by the way, this is also finite. This is a finite language. Final one, set of all strings that start with A. All the strings that start with A that are formed over sigma. එතකොට මෙයාට මොනවද එන්නේ? We can have A. It should start with A, so we can have A alone. Then A. Again, it starts with A. Then we can have AB. එතන පළවෙනි එක නෑ ඉවරයි, දෙන්න ඉන්න එක ඉවරයි. Now we will come to 3. We can have AAA. Then we can have AAB, ABA, ABB starts with A. Then we can have now now if we look at this in a pattern, we have the singular ones, then the ones that are in a pair, then the ones that are together with three people, then I mean we can go on and on with 4, 5, 6 likewise. So this doesn't end. Yeah, so we say that this is an infinite language. So you see, we can have finite languages or we can have infinite languages. So a language which can be formed over a particular sigma, okay, a language which can be formed over a given alphabet could be either finite or it could be infinite. Okay, it contains a set of symbols that are formed, sorry, it contains a set of strings that are formed over a particular alphabet, and it could be finite or infinite. Right, so that is about languages, and then we move into so before we go to that, now in this triangle we talked about languages as well. Okay, so this is the flow chart, the basic flow chart that we can talk about in automata theory. Okay, now we are going to talk about certain operations that we can perform on strings. You have heard of these as well. So string operations. The first operation that we are gonna talk about is concatenation. You know what concatenation is? We basically link strings together in concatenation. For example, say we have an alphabet with A, B, and another alphabet with C, D. Then we can concatenate and generate strings like that. Then the next one is we can talk about reversal of a string. Reversal. So if we have a string W, which is A1, A2, A3 up to AN, we can get the reversal of the string where we have AN, AN minus 1, AN minus 2 up until A1. Okay. The next one is the length of a string. So we know what length is. We discussed in the morning, morning as in when we began the lecture, we said that the length of a string can be taken by the absolute value or modulus. So if we take the same string W, length of W will be the absolute value of W modulus W. And thereafter, we talk about a substring. So substring kila kiyanne, we extract a set of characters from a given string. When we are given a string AB, we can extract a set of characters from this and create a substring. So the substrings that we can create over this particular string W, it could be null, it could be a null string, and then it could be A, B, or AB. Okay, extracted set of characters out of a given string is called a substring. Finally, we can talk about an empty string. Empty string, null string, ඒ කියන්නේ මොකුත් නැහැ, length is 0. ඕක අපි symbolize කරනවා, we use epsilon. Okay, ඒකම තමයි මෙතනත් දැම්මේ. So this means length of this string equals to 0. Okay, so when it is 0, we symbolize it by epsilon, or sometimes we use lambda as well. Okay, so these are the string operations which we will talk about. Okay, concatenation, reversal, length, substring, and empty string or null string. Okay, so far we discussed about what did we discuss about? We discussed about a symbol, then an alphabet, then a string, then languages. Then we spoke about some mathematical preliminaries where we spoke about sets, sequences, and stuff. And thereafter we spoke of number of strings of a particular length that we can form, and then um, we spoke about this string operations. Okay, now we move on to talking about powers of sigma. Okay, what are the different powers that we can talk about when it comes to sigma, an alphabet? So I'll start with an example. Let's say for this entire topic, I'm going to use sigma to be AB, the alphabet to be AB. So this has two characters, two symbols. So the length of the what do you call the alphabet is 2. Okay. Now, as number 1, I'll take sigma to the power of 1. Sigma to the power of 1, which means set of all strings that can be formed over sigma. Sigma means this alphabet, which are of length 1. Out of the set of all characters we can form over sigma of length 1. We discussed this earlier as well, so I hope you can remember. So it's either A or B. Echo A, echo B. So if I symbolize this, now I have two symbols, two strings here. So if I denote this with respect to the length of sigma, I can say this 2 to the power of 1. එතකොට sigma ගේ length එකේ power එකට එන්නේ length of the string. Okay, right, then I'll say number 2 is sigma to the power of 2, where we talk about set of all strings that can be formed over sigma which are of length 2. Okay, I'm not going to write that entire thing, I'll just write length 2. So here what happens is sigma gets concatenated with itself 2 times. That is why we spoke about these string operations before we go to that powers of sigma, because we need concatenation there. So what happens is sigma gets concatenated with itself. AB gets concatenated with AB. Okay, so the answers we get AA, AB, BA, BB. Okay, so here we have 4 strings, which is 2 to the power of 2. Then number 3, sigma to the power of 3. That means length of all, a set of all strings that can be formed over sigma which are of length 3. So by this pattern that we even discussed before, you can say that this will have 2 to the power of 3 strings, to the power of 3 strings, which is, we can come up with 8 strings. Okay, so likewise we can go up to n, sigma to the power of n, where we say that this is the strings of length n that we can form over sigma. The Matica we have discussed before as well in the morning when we began the lecture. Now the new thing that we are going to discuss is sigma to the power of 0. Sigma to the power of 0. Okay, so this means, just like what we discussed, this means the set of all strings that we can form over sigma which are of length what? Length 0. Power eka is the length of the string, so this is length 0. So this is what we call the null string and this is the smallest string that we can form, the smallest string. Okay, and we can symbolize this by using epsilon or even lambda. So we can say that sigma to the power of 0 is equal to the null string. Okay, right. Then we come to talk about something important which goes in the same flow. Sigma star. Okay. Now sigma star kiwahama, you can replace this star with any digit you want. That is basically what happens. Which means you can put 0, 1, 2, 3, whatever in place of this star. So we say that sigma star is the collection of, or the union of 0, 1, 2, 3, or everything. It's the union of everybody whom we spoke about over here. Megolange, ඊට පස්සේ ඔහොමම දිගට දිගට යන හැම එකකම union එක is sigma star. Okay. So in English, if we define this in simple English, this is the strings that we can obtain of all lengths over a particular alphabet. Set of all strings possible over an alphabet is called sigma star. So we give this a name. We call this the clean closure. Clean closure, නැත්නම් star closure, So this is the set of all strings of all lengths possible over a given alphabet. This is like the universal set. So it kind of works like the universal set. Is that clear? I hope that's clear. Okay. Now, now we are going to combine sigma star with languages. Okay, so now we said that sigma star is the set of all possible strings over sigma. එතකොට අපි කලින් languages ගැන කතා කරනකොට උදේ මේකට කලින් when we spoke about languages, if you remember, we defined 3 languages, L1, L2, L3. These two were finite, this was infinite. So we defined these 3 languages on sigma. Sigma can alphabet we defined L1, L2, L3. Okay. So these 3 languages contain strings which can be formed on sigma. Okay, so they contain strings which can be formed on sigma. Okay, and what is sigma star? Sigma star means all possible strings that can be formed over sigma, which means, do you understand that L1, L2, L3 are parts of sigma star? Parts or subsets of sigma star. මේ තුන් දෙනාම මෙයාගේ ඇතුළේ ඉන්න කට්ටිය. Because this person is the one who contains all possible strings that are formed over sigma. මේගොල්ලෝ define a certain set of strings that can be formed over sigma, which means these people, L1, L2, L3, are parts of this universal set. Okay, or subsets rather. So we say that L1 is a subset of the universal set, L2 is a subset of the clean closure, L3 is a subset of the clean closure. Okay, so sigma star contains all possible strings of all lengths that are formed over sigma, and languages contain a certain subset of strings that are formed over sigma. Because of that, a language is a subset of sigma star. එතර දැන් අපිට තව විදිහකට languages define කරන්න පුළුවන්. අපි මුලින්ම languages define කළේ a set of substrings කියලා. Sorry, a set of strings කියලා. We said language. A language is a collection of strings කියලා කිව්වා අපි කලින්. Collection of strings. Now we can say that a language is a subset of strings that belong to the set of all strings defined on an alphabet. A language is a subset of strings that belong in the subset of all strings that are possible on an alphabet. Subset of all strings කියලා කියන්නේ මේ කියන්නේ sigma ගැන, sigma star ගැන. ඒතර ඒකේ subset එකක් කියලා තමයි කියන්නේ කවුද? Language. Right. So I hope that part is clear to you. Okay. Before we move on to the next part, we have a variation of the same thing. ඒකට අපි කියනවා sigma plus කියලා. Positive closure. අරක star closure, this is the positive closure. Okay, so the positive closure means now here in sigma star we had sigma to the power of 0, sigma to the power of 1, 2, 3 ඔක්කොමනේ. ඒ කියන්නේ if we symbolize this using characters, using symbols, sigma to the power of 0 කියන්නේ null string. Union sigma to the power of 1 කියලා කියන්නේ A or B. Power of 2 means AA, AB, BA, BB. This goes on and on and on. So this entire thing is sigma star. When we come to sigma plus, the positive closure, what happens is this gets removed. The first one is not there. So which means positive closure is equal to sigma to the power of 1 union, 2 union, 3 union. Without the first one, we have the rest of it. Okay, it goes on and on. So we can symbolize this by saying sigma plus is equal to sigma star minus the sigma 0th power minus the empty string. That is the only thing which is not inclusive in the positive closure. Okay. Are you clear up to that part? So what have we been discussing? We started with symbols, which is the basic building block. Okay, they get together and create an alphabet. Then a sequence of symbols formed over an alphabet is a string. Then a set of strings create a language. Okay, Then we spoke about number of strings of a particular length that are possible over an alphabet. Then we spoke of set sequences and stuff. And then we came to talk about a language, and we defined three languages, and then we spoke about string operations, concatenations and stuff. ඊට පස්සේ we spoke of powers of sigma, where we defined sigma to the power of 0, 1, 2, 3, and then we defined sigma star, which is the clean closure. Clean closure can be defined languages in a different way, because we found out that a language is a subset of clean closure, because sigma star contains all possible strings of all possible lengths that can be formed over a alphabet or an alphabet, and language defines a certain set of those strings. Because of that, a language becomes a subset of all possible strings that can be formed over an alphabet, which means a language is a subset of sigma star. Then we defined the positive closure, sigma plus, which doesn't include the null string. So we define this by saying sigma star is, sigma plus is equal to sigma star minus the null string. Okay, now since a language is a set, we said that a language is a collection of strings. So a language is a set of strings. Because of that, we can perform all the operations that we perform on sets on languages as well. Language එක set එකක් හන්ද sets වල තියෙන ඔක්කොම operations we can perform them on a language as well. So union, intersection, difference, complement, everything can be performed on a language. Complement ගැන කතා කළොත්, if we perform complement operation on a language, so L dash is equal to what? Now this is the universal set, and say we have L. So what is L dash? L dash is equal to sigma star minus L. Okay, and we can define the same operations on a language just like we did on sigma. So L to the power of 0 is the null, and then we can perform L star just like before. There's no difference here, and the positive closure is the same like before. Okay, right. Okay, okay, so now look at this. We can categorize languages into two parts. We have natural languages and we have formal languages. So a natural language is difficult to define, okay, whereas a formal language is defined precisely, okay, so that we can perform analysis on it. So some basic problems that we might encounter when we work with languages is how we can define this language properly, accurately, and how to use those definitions that we have done on the language in an efficient way so that we can generate a reliable program. Okay, and the theory of a language, what we discuss in this lecture series, the theory of a language, these are used in defining a language at the same time when we construct translators. Okay, and yeah, we discussed this powers of a language. Okay, then methods of defining a language. So we have two methods in which we can define a language. We can either list out all the possible words all the possible words or all the possible strings of a particular language. We can do that if the language is finite, of course. And the other method is we can give a set of rules which define acceptable strings. Okay, මේ මේවා විතර accept කරන්නේ කියලා we can give a set of rules, right? So here again we give the definition. A language L over an alphabet sigma is a subset of sigma star. Thus, set notations can be used to define a language, which we discussed before. But the problem is set notations might not be sufficient sometimes when we want to define a complex language. එහෙම වුණාම we have to use something else. So what is this something else that we use? We use something called a grammar when we want to define a complex language and whenever set notations are not adequate. Okay, so a grammar is a mechanism which is better, which performs better when defining a formal language. Okay, right. So before we move into a grammar, let's discuss what a formal language have. A formal language has, okay? So a formal language will definitely have an alphabet. That's understandable. An alphabet which is finite and non-empty. Then it has a syntax. Syntax කියලා කියන්නේ the linguistic form of a sentence. Okay, it's only concerned with the form, not the meaning. තේරුම වැඩක් නැහැ syntax තනියම ගත්තාම. It's just the form of the sentence. For example, අපි කියමු මෙහෙම sentence එකක්. This is the most popular example when it comes to this. Colorless green ideas sleep furiously. Okay, now you see here there are no grammar mistakes here. Okay, so this is grammatically correct, but there's no meaning here. Okay, so syntax only focuses on the form of the sentence, the form of the set of words or strings, and not the meaning. Whereas semantics, which is the next one, is concerned about the meaning, the linguistic meaning of a sentence. Okay, so a syntactically correct sentence, a syntactically correct program rather, might not be always meaningful, or it might not always be semantically correct. Okay, just like the example that we have written over here. All right. Okay. Hi. Then අපි යනවා to talk about the definition of a grammar. Okay. Now let's define a grammar. The definition of a grammar. Okay, so now let's say this grammar is G. Let's symbolize it by G. So G can be denoted using 4 parameters: V, sigma, SP. Now let's define these. V කියලා කියන්නේ, G is the grammar. V stands for the finite set of non-terminals. I'll explain what this is. Okay, finite set of non-terminals. Then we have sigma. You know what sigma is? Sigma is the symbols, the alphabet. We call that the terminals. Finite set of terminals. You can just say, I mean, for understanding purposes, we can say this is the alphabet. Then we have an S, which denotes the initial non-terminal. Initial non-terminal කියලා කියන්නේ initial කියන්නේ පටන්ම ගන්න එක. That's where we start from. Okay. So අන්තිමට P is the finite set of productions. Okay. Now let's go through these one by one. So finite set of non-terminals. Non-terminals means, I'll take an example and explain this. So let's say, just take an example. So you have one place over here. Capital A is a place, or a state rather. Then you have capital B, that is another place, another state. Okay, you can be in two states. Whatever. And then මේ තැන් දෙක connect කරන්න A ඉඳන් B ට යන්න you have a terminal. Terminal එක ඇතුලෙන් තමයි යන්න තියෙන්නේ A ඉඳන් B ට. And let's say the terminal carries simple A. So you can go from A to B through the terminal A. Okay. So here A and B come under non-terminals. These are the states. Okay, the definite places we can go from one to another through a terminal symbol, endpoints rather. Then what this S means, now sigma in this case is A, which is the terminal. Okay, he's the person who will connect these two endpoints. He's the one who's going to take us from A to B. And then S means the initial non-terminal. Initial non-terminal kind of where we start with. So let's say, for example, if A is the place where we start from, then A is going to be the initial non-terminal, the starting place. So you understand that S should be there in the set of V. Okay, so S should be an element of V. S should be there. Okay, right. Then P, finite set of productions. What is this term productions? Let's discuss what a production is. I hope these three are clear. What a non-terminal is, what a terminal is, and what the initial starting state is. Finally, we have P. P means production. So what does that mean? So to talk about productions, let's take an example. Okay. Let's say we have a string W. W kila string එකක් ඉන්නවා. මේක ඉන්නවා UXV. W string kila කියන්නේ UXV. Okay. Now the production rule that we have, the production rule, let's say අපිට production rule එකක් ඉන්නවා X Y. Now this is the format of a usual production rule. Okay. X, how we say this in English? In English is X translates to Y. Okay. So X translates to Y is a production of the grammar that is given to us. Okay. So what this production rule will do is it will replace any of the X's that are present in the string by a Y. X line nona, එතනට ගිහලා Y දානක තමයි this production rule is gonna do. Okay. So basically, since our string is UXV, my production rule like දැම්මහම what will happen is this will get converted to UYV because it basically replaces all of the X's in the string by Y. This is the production rule given for that particular grammar. Okay. So we say, now when this translation happens, we say that we derived uyv from uxv. That's understandable. Api make we derived this by this. Meken tha make aave apita. Yeah. So this is the derivation we got. That is the answer we got, the derivation. So we say uxv derives uyv, or we say අනිත් පැත්තට කියනවා අපි uyv is derived by uxv. හරිද? Either uxv is derived, uxv derives uyv. එහෙම නැත්නම් we say uyv is derived by uxv. Okay. Either way, this is the derivation we got. Okay, so basically what a production rule will do is whatever is there in your left hand side gets translated to whatever is in the right hand side. That is what basically happens. Okay, එතකොට දැන් මේ production rules දාලා what we can do is we can derive a new string from a given string. Okay, when we are given a particular string, we can derive a new string using the production rule. That is what the production rules in a grammar basically do. Okay, then now when we keep on applying production in an order, say we have now the string that we had is w ne, then go අපි production rules දාගෙන යනවා. ඔන්න අපි එකක් ගන්නවා w2. ඒකට තව එකක් we use another production rule, we get w3, we use another, so we go on until we can go on. Yeah, so wi me ඔක්කොම w ලා they are the derivations we get. Okay, w1 derives w2, w2 derives w3, w3 derives w4. It continues, it perpetuates. Okay, so these answers that we get, the derivations we get, are called sentential forms. These derivations are called sentential forms of the derivation. So this is a word that we give. We say these are sentential forms. Basically the derivations වලට තමයි අපි කියන්නේ ඔය වචනේ. හරිද? Okay. Then දැන් අපි ගමු sentential forms ටිකක්. මේකට අපි උදාහරණයක් ගමු. අපි කියමු let's say we have a grammar which is defined by these four SP. Let's say it's defined like this. So the set of non-terminals are AB. Let's say the set of terminals are AB, simple AB. And then let's say the starting symbol is A, starting non-terminal. And then the productions, let's say the productions are, we have one production, A translates to AA, simple A, capital A. Or A can translate to B. This vertical line is to symbolize O. Right? If there A innona, you can replace that by AA, or you can replace that by a B. This vertical line is to symbolize O operation. Okay, so this is one production rule. Then let's take another production rule. Let's say B translates to AB or the null string. So these are the production rules that we have. Full grammar declaration. Okay, so this is an example grammar that we have defined. Okay, now let's see what the derivations we get are. Derivations, sentential forms balanda yan. So let's start with A. A වලින් start කරන්නේ. The initial symbol is A, initial non-terminal is A. So we can translate A to AA. How? Because it's given in the production rule. ඊට පස්සේ ඔන්න ආයේ ඉන්නවනේ අපිට A. We can again translate this A or replace that A by either AA or B. So I'll use B this time. I'm going to replace A with B now using the production rule. හරිද? Let's make this B. එතනට අපි B දාමු. B. Then now we have AB. Now I have a B over here. I can replace this because I have production rule for that as well. So I'll replace this B with BB. A, B වෙනුවට දානවා එයාගේ derivation එක. හරිද? ඔන්න දැන් මට එනවා ආයේ B කෙනෙක්. So I can derive something again. I can replace this B again. අපි ආයේ දාමු මේකම දාමු. In place of capital B, I use again a BB. හරිද? Again I can do the same thing because I have another B. I can again do the translation. I can again do the derivation. I can replace capital B. This time I'll replace it by the null. So I am resulted with AB B. That's the end of it. There are no non-terminals. There are no other non-terminals left in this particular derivation. Because of that, there will be no any other derivation. So this is the end of it. So you see, we got a set of derivations. Hari? ඔය set එකටම අපි තමයි අපි කියන්නේ මොකක් කියලාද? Sentential forms. හරිද? This is a sentence. Sorry, all of these are sentential forms. That is what we said over here. All the W's, WI, W1, 2, 3, up to N are called sentential forms. They are the derivations that we get by applying production rules. There another. එතකොට දැන් මෙතන අපිට කිසි අවුලක් නැහැ because you know, in all of these derivations, in all of the derivations, there was only one non-terminal. එකම variable එක අපිට ආවේ. There was only one non-terminal. Because of that, we didn't have a choice of which non-terminal to choose when we are going to derive the next sentential form. එකයි නින්නේ යාව තමයි දිගාරින්න ඕනේ. Okay? Here we had only A, here we had only B, here we had only B likewise. And when there are no non-terminals, that's the and we don't expand it next. Okay, so there is no choice as to which variable or which non-terminal to expand next. Okay, right. So let's go back and see what we discussed so far. Languages වලට පස්සේ up to languages, I think you are okay with that. Flow එක මතක ඇති. Languages වලට පස්සේ අපි කතා කළේ මොනවද? We spoke about grammars. We defined a grammar, and then we defined what a sentential form is, and then we spoke about before that we spoke about natural languages and formal languages and some problems that we encounter when we work with languages. Okay, and we defined the powers of a language: L to the power of 0, L to the power of 1, L star, L plus and stuff. And we said that we can define languages in two ways. We can either list out all the words in the language, or we can give a set of rules saying මේව තමයි අපි accept කරන්න කියලා. These are the words that are acceptable. So then we said that a language is a subset of sigma star on the alphabet sigma. So we said set notations can be used over a language because it's a set, and whenever set notations are not enough for us to define a language, where the language is complex, we use something called a grammar, which is a powerful mechanism to define a formal language. Okay? ඊට පස්සේ තමයි we defined a grammar using V sigma SP. We discussed what a V is, what sigma S, and then we discussed what production rules are. With production rules, we came into sentential forms. Okay? A flow එකේදී අපි තාලකක් කතා කළා formal languages වල the things that are present in a formal language. We spoke about an alphabet, syntax, and semantics. Okay, and we said that syntax only talks about the form. අපි උදාහරණයක් දුන්න colorful මොකක්ද මේ colorful green ideas sleep furiously. It was grammatically correct, syntactically correct, but there was no meaning. And then we said the semantics is looking into the linguistic meaning of the syntactically correct sentence. Okay. Okay, before we move into the next section, can you all please log into the VLE and go to the course page? There are two simple questions which I have uploaded under the first topic. I want you to submit the answer for that. Submit the answer for that now. In the bank me දාන්න දැන්. Okay, on the introduction to automata theory, you have day 1 killer quiz. Can somebody tell me if it's visible to you all?
Yes, no, it's visible.
Okay. Can you all please try it and submit the answer quickly? Two questions, two simple questions, just what we discussed now. Grammar ගැන එකක් ඇති, ආයේ language ගැන එකක් ඇති. We define languages in two ways. One, we said it is a set of strings. ඊට පස්සේ පහ වෙලා අපි කිව්වා language is a subset of set of all strings of all lengths that can be created over a sigma කියලා. Then we defined a grammar using four things: V sigma SP. Now let's talk about why we use grammars. You know, we usually use them when we want to develop a parser, which you will study in a future lecture probably. And sometimes it's hard to develop a parser using certain grammars. Okay, so in that case, this may be transformed into equivalent grammar that can be parsed. Okay, these things you will be we will be discussing in the future lectures. And by the way, if we denote a grammar by G, which we usually do, G කියලා නම් we denote a grammar, then the language denoted by the grammar, the language of this particular grammar is given by L of G. Okay, so just give them in mind as well. And just like what we discussed under strings before, do you remember when we were doing two equivalent strings, I said S1 may be equal to S2 in the case of their letters being equal and the order being equal. Just like that, here also we can say that two grammars are equal, they are equivalent to each other if they generate the same grammars. Okay, so sorry, if they generate the same language. If there are two grammars G1 and G2, if the language they generate, meaning LG1 and L of G2 are equal, then we say that these two grammars are equivalent. It's the same story that we discussed under strings as well. Okay, right. Now let's talk about a small example. Let's take, now we are talking about languages and how we, grammars and the language that they define and all. So let's take an example language. Earlier we took the English language for an example. Now we are going to take the Pascal language for an example. Okay, so now this language is a set of strings with letters. Okay, now okay, let's give this a formal, not a formal, informal definition. Nikan api Inggrisiyen kiyamu. Informal definition එකක් අපි කියමු. So this includes set of strings with a letter followed by an arbitrary number of letters or digits. Okay, so which is to say that this includes strings where you first have a letter, strings with a letter, letter එකක් තියෙනවා. ඊට පස්සේ this is followed by any number of, arbitrary number of letters or digits. එකන ඊට පස්සේ එන blanks වලට you can fill these blanks with either letter or a number. Percent of letter or a number නෙමෙයි digit. Letter or a digit. Letter or a digit, okay? So this is how we give the informal definition for the strings of this language. Now let's give it a formal definition. Formal definition of the grammar. Okay, so here api me V sigma දාගෙන මෙතන කළේ, this is the formal definition of a grammar. This is the formal definition. Okay, right. So we are given the formal definition. Then අපි කොහොමද කියන්නේ? දැන් ඔන්න අපිට ඉනවා string එකක්. Some string which we denote by ID. එතන මෙයාගේ කොහොමද format එක යන්නේ? මෙන්න මේක බලාගෙන කරමු අපි. First you have a letter. Okay, මුලින්ම you have a letter, this one. And the letter is followed by rest of the string, rest of it. Whatever it is, we don't care, it's the rest. පළවෙනි මේක ලියනකොට we don't care about the rest, we just say rest of it. හැබැයි අපිට නිකන් ඉන්න බෑ. We can't just stop there. We have to say what this rest is. Okay? So in the next rule, we say what is rest. මොකද මේ rest කියන්නේ? يعني දැන් අපි මෙයාගේ කතාව ඉවරයි. මෙතනින් එහාට මෙතන ඉවරයි. දැන් මෙතනින් එහාට යනවා අපි. Okay? We go further and now we are going to define what rest is. So what can rest be? Rest එකේ ඉන්නේ මොනවාද? You can either have a letter or a number in the rest of it. Letter or a digit. එක්ක letter එකක් එක්ක digit එකක්. You can have a letter or a digit. Now in the first case, if we take a letter, then may blank set එක මම වෙනම ගත්තොත් මෙතනින් කඩලා මේ ටික මම වෙනම මෙතෙන්ට ගන්නම්. හරිද? එතන rest හරිද? මෙහෙම blanks ඉන්නවා නම් in the rest, if the first one was a letter, now out of letters and digits, I chose letter. In that case, if this is the starting point now, then the rest of that is going to be the letters or digits. Letters or digits. Letters or digits. එක තේරුණාද? බලන්න. ඔන්න දැන් blank set එකක් ඉන්නවා. First one is a letter, we know that it is given. So what we said was, these people can be the letters or numbers. That's what we said. And so on. Okay? Now, this first one is already written over here. So that part is gone. Then that is gone. Now we take the rest of it. This part. In that part, if we choose the first one to be a letter, if this is a letter, then this is and that could be a letter or a number again. Number name digit, okay? So let's write that first. The rest of the first one, this is the first one, that could be, first one could be a letter, it could be followed by a number. Number name, rest. Okay, first one is a letter, it could be followed by the rest of it. We don't know what the rest is. This is not the only case though, because in this case I chose the first one, I can choose the second one as well. So in the second case, if I choose a digit first, then rest I can again put letter or a number, letter or a digit. Okay, so this could be the case, or vertical line or ek ho, what is the other one? Digit and rest. There another digit and rest. එහෙමත් තව එකක් වෙන්න පුළුවන්. මොකද අනිත් එක? letter එක විතරක් තිබිලා මේකේ rest එක ඔක්කොම මුකුත් නැති වෙන්න පුළුවන්. So in that case it could be null as well. Got it? Hi. Then I අපි මේ rest ගැන කියන්න යනවද? නෑ, because why? We have defined a rest already. So this is kind of recursive. මෙතන rest එක I define කරන්න ඕන නම් මේ rest එකම අරගෙන මේ rule එකම දාන්න පුළුවන්. Okay? එතකොට වෙන්නේ මොකද්ද? I දැම්මොත් එහෙම මෙතනින් කඩනවා. මෙතනින් කඩලා මේ blank එකට letter එකක් දාලා ඉතුරු ටික rest එක කරනවා. එක මේ blank එකට digit එකක් දාලා ඉතුරු ටික rest karna. You break over here, you put a letter over here, you go on, put a digit over here, you go on. Got it? So however many times you have the rest, you can keep on translating or repeating the same rule and getting derivations. Got it? But the thing is, rest define we have to define somebody else. Who's that somebody else? We have to say who letters are and who digits are, because even though we know what they are, the computer doesn't know who they are. So we have to say who is a letter. Letters one other, either A, O, B, O, C, up until Z. Finally, who is a digit? A digit could be either 0, 1, 2, so on up until 9. Okay, so this is a formal definition of the grammar given to the informal definition that we gave for the grammar of Pascal language. Got it? So this is an example definition of a formal grammar that we did. I hope you understood that. Okay, and with that, we come to the final part of the lecture, where we introduce a person. We're going to talk about a person here. You might have heard of this person. This person's name is Noam Chomsky. මෙයාගේ නම තමයි Noam Chomsky. මෙයා මොකක්ද කිව්වේ කියලා තමයි දැන් අපි බලන්න යන්නේ. So what did this fellow said? What did he say? Okay. So this person said, I mean, like not said, he actually defined a hierarchy of formal grammars. Okay. Rather classes of grammars. We call this Chomsky classification of grammars, Chomsky's classification. Okay, so he defined 4 classes of grammars, saying type 0, type 1, 2, and 3. Okay, so basically this is what we will be discussing in the future lectures. You will be discussing, I mean, like we will be discussing all of these, you know, context free, regular, and stuff. Okay, so what did he say? He came up with classes of, I mean, 4 classes of formal grammars or hierarchies of grammar. The first one, he named it type 0. Type 0. Like he's the mother of all. He contains, type 0 contains all the formal grammars. Okay, so it contains all formal grammars, and as you see here, it can be in the form alpha. It can be in the form alpha translates to beta, where alpha is a string of terminals and non-terminals. Again, there could be terminals sigma and non-terminals v. Okay, it could contain both, just like here. Do you see this? Then alpha to beta kila kiyane megolo alpha megolo beta ne. So you see alphas could be string of terminals and non-terminals. Okay, terminals, and these are non-terminals v's. Okay, and then with at least one non-terminal, adugani it should have one non-terminal, meaning there should be at least one non-terminal on that side, meaning there should be at least one v. And beta is a string of terminals and non-terminals, and there are no such what do you call rules saying that there should be at least one of this or that. Okay? So this could be either v or sigma, and this could be the v or sigma. This should definitely have at least one non-terminal. So this is what he said about type 0 grammar, which is the first class. And this is unrestricted, like all formal grammars are inclusive in this. Okay, and this can be recognized by a Turing machine, the automata. Automata theory. Automata is the plural word, the singular one is automaton. Okay. Then type 1 grammar. Type 1 grammar context sensitive. We'll be discussing about that later. So the productions should be of the form alpha A beta, alpha gamma beta. A non-terminal එකක්. හරිද? There's alpha beta gamma set එකම. It could be either a non-terminal or a terminal. එක තමයි මෙතන මේ කියන්නේ. මේක කැලලක් මෙතෙන්ට ගිහින් තියෙන මේ bracket එක ඇතුලෙන් කියන්නේ. So it is a string of terminals and non-terminals දෙකම තියෙන්න පුළුවන්. Okay, just like this. See, so it could be a string of non-terminals and terminals on the right hand side. Okay, so alpha and beta may be empty. Okay, alpha, beta, this can be empty, but gamma cannot be empty. That means there has to be at least one there. Okay, so then we have another rule here in type 1 grammar. The same rule repeats in type 3 as well. මෙන්න මෙහෙම null එකක් තියෙනවා නම් තියෙන්න පුළුවන් as long as this non-terminal doesn't appear on the right side of any rule. ඕනම rule එකක් ගත්තහම දැන් හිතන්නකෝ මෙන්න මෙහෙම rule එකක් ඉන්නවා නම් හරි මේක යටින් මෙහෙම එකක් ඉන්නවා කියලා හිතන්නකෝ ඉන්නවා ඉන්න පුළුවන් as long as this non-terminal doesn't appear on the right side. මේක අස්සේ එන්න බෑ ඒක. ඒ කියන්නේ අපිට තියෙන්න බෑ A B B R වගේව තියෙන්න බෑ දකුණු අත පැත්තේ. එහෙම නැත්නම් we can have this type of productions as well. Okay, right. So these can be recognized by linear bounded automata. Next one, type 2. Type 0 තිබුණා, type 1 තිබුණා, දැන් අපිට ඉන්නවා type 2. මේකේ මොකද වෙන්නේ? These are in the form A implies, sorry, not implies, A translates to gamma, where A is a non-terminal and Y is a string of terminals and non-terminals. මේ පැත්තේ ඉන්න එකම එක non-terminal එකයි. තව ඉන්න බෑ. මේ පැත්තේ ඕන කට්ටියට ඉන්න පුළුවන්. Okay. So this is recognized by non-deterministic push-down automata. Okay. Okay. And they generate grammar accepted or context-free. Those will be coming in future lectures. That is type 2. Okay. Now we have type 3 grammar. So type 3 grammar actually has two forms, which comes in the next slide. So type 3 grammar must have, okay, they must have a single non-terminal on the left-hand side. They ඔක්කොම යන අර මං කලින් කිව්වා වගේ LHS RHS විදියටනේ. And right-hand side consisting of a single terminal or a single terminal followed by a non-terminal. Okay, you can either have a single terminal or single terminal followed by a non-terminal. ඒ කියන්නේ මෙතන ඉන්න non-terminal symbol එකක් එක්ක මෙහෙම translate කරන්න පුළුවන්. එක්ක එක මෙහෙම translate කරන්න පුළුවන්. ඔය ඕක එන විදිහට තමයි අපිට forms දෙකක් හැදෙන්නේ. හරිද? මේක මේ එන විදිහට we have two forms. We have right linear and left linear, which we'll be discussing in the next slide. Right linear and next left linear. So before we go to that, the production must be in the form x implies a, x implies a y, where x, y is terminals and sigma is, sorry, a is an element of sigma, sigma is a terminal symbol. Again, as I said before, the type 1 rule applies. R implies not implication. R translates to null string can be allowed if this person does not appear in the right hand side. Hari? Right එකේ ඕක නැත්තම් විතරක් ඕක allow කරන්න පුළුවන්. Right එකේ අයින්නවා නම් it's not allowed. That is type 3. Okay, now we come to the classifications or two categories of type 3. Right linear or left linear. Okay, so right linear කියලා කියන්නේ all the productions are of the form A implies AB. Your non-terminal is towards your right. පුළුවන් තරම් එක right එකට යන්නේ. Okay, තනියම ඉන්නවා නම් ඒක වෙනයි. If there are what do you call non-terminals, they mostly go to towards the right hand side of the equation. And then left linear means as much as possible they come towards the left hand side of the production. Okay, so it's like this. So you can have x is AA, capital A. If it is towards the right, we say this is right linear. If it is towards here, we say this is left linear. That is how we categorize that. And so these grammars are regular grammars, which again we will be discussing, and the automata is finite state automata. Okay, so then you see there are regular grammars, there are context-free grammars, context-sensitive, and unrestricted. Unrestricted recursively enumerable, like all four. Okay, so if we represent this in a sort of a diagram, so if we say if we come up with a set inclusion of Chomsky hierarchy, the smallest one is going to be regular grammars, the type 3 people. However, then you have context free, the type 2. Okay, ඊට පස්සේ you have context sensitive. This is of type 1, type 2, type 2, type 1, type 3, everything, type 2, type 1. Finally, you have the locuma one, which is type 0. Okay, so this is like a set inclusion. I mean, like how you represent the 4 classes that he identified, that this person identified in a set. Okay, so recursively is the type 0 is the main person who will include all of the classifications. All right. Okay. And we can generalize this classification, Chomsky's classification, by saying a language is said to be of type K if it can be generated by K type grammar. Okay. Right. So let's do a quick recap on what we did today in the very first lecture. We started with the basics of the subject, symbols, which includes A, B, or whatever, and they are the basic concepts, not the basic concept, basic element of the automata theory. And then they get together. Set of symbols is an alphabet, sigma, and then a sequence of symbols that are formed over an alphabet is called a string. There's a string king, a collection of strings becomes a language, and then we spoke of strings of different lengths that we can form over a particular alphabet. Remember, strings are always formed over an alphabet. if it is a language, it has to have an alphabet which includes symbols. ඒක උඩ තමා strings හදන්නේ ඒ language එකට. So we discussed about strings of different lengths that we can form over an alphabet. එකෙන් අපි ආවා sigma to the power of n මෙන්න මේකට. That is how we got there. Sigma to the power of n. This is the general form of identifying how many strings can be formed on a particular alphabet sigma of strings of a particular length. Okay, so this power n is the length of the string. We discussed about that, and then we went on to discussing mathematical preliminaries because we came across certain words like sets, sequences, and stuff when we spoke about alphabets and strings. So we defined set, sequence. This is where we spoke of two strings being equal if the letters are equal and the order is equal. And then we spoke about tuples, and we said 2 tuple, 3 tuple, 4 tuple, and finally we said k tuple. And by the way, when you have a 2 tuple, you call this a pair. 2 tuple is given a special name called pair. And then we spoke of Cartesian product, that of course you know already. And then we went on to talking about languages, and we defined three example languages on alphabet we took, L1, L2, L3 කියලා. L1 and L2 were finite, while L3 was infinite. And then before going into the next part, we spoke about string operations like concatenation, reversal, length, substring, empty string, and all. We discussed that before moving to the next part because we needed this concatenation for the next part. එතකොට ඊළඟ part එකේ අපි කතා කළා powers of sigma. එතකොට අපි කිව්වා sigma to the power of 1 කියලා කියන්නේ set of all strings that can be formed over sigma which are of length 1. Then sigma 2, we said sigma to the power of 2 means sigma gets concatenated with sigma. So these are the strings of length 2 you can form over this alphabet. So it perpetuates sigma 3, sigma 4, same thing, and you can find how many strings you can generate in that particular length using the the expression that we found out. Then we defined sigma 0, which gives us the null string. ඊට පස්සේ we came to the important point where we discussed about sigma star, which is the clean closure or the star closure, which is the person who includes all the strings of all lengths that can be formed over a particular alphabet. So it's a universal set. Through that, we came to another definition of a language. We said that a language is a subset of the collection of all strings that can be formed over a particular alphabet. එතකොට මේකේ අග කෑල්ල all strings that can be formed over an alphabet කියලා කියන්නේ sigma star කියන එක. එතකොට language කියන්නේ L කියන එක. එතනින් අපිට එනවා L is a subset of sigma star, whatever the language it is. Okay, with that we defined sigma plus, the positive closure, which does not include the null string. Sigma star කොම null string එකක් ඉන්නවා යාගේ. Sigma plus කිව්වහම null string එක නැහැ යාට. So that is defined by saying sigma star minus null string. Okay, then we define some operations on languages where we talked about union, intersection, difference and stuff. Then we defined the complement and then powers of a language, just like we did for sigma. ඊට පස්සේ තමයි අපි define කළේ grammars, formal definition of a grammar. V sigma SP, we defined non-terminals, terminals, starting terminal and productions. Productions වලදී අපි කිව්වා මොකක් හරි string එකක් production rule එකක් through ගෙනියලා we can generate a new string. Okay, So production rules are basically working or from the left hand side towards the right hand side. Whatever is in the left hand side will be replaced by the right hand side. So we can apply production rules in any order, and the answers that we get, the derivations that we get, are called sentential forms. Okay, so we said that uyv is derived from uxv, or uxv derives uyv. All the derivations as a collection are called sentential forms. And ඊට පස්සේ අපි එකට example එකක් ගත්තා. We took Pascal language as an example, and we gave an informal definition saying that it includes letters followed by any number of letters or digits. Again, we gave it a formal definition like this. So I hope that was clear. ඊට පස්සේ තමයි we came into this person's classification of grammars. So this guy classified grammars under 4 categories, type 0, 1, 2, 3. We discussed how these grammars can be represented, the rules, the production rules and all. And then we represented that in a, in a set format, in a set inclusion. Okay, right. So yeah, that is the end of the lecture today. I hope that was clear. I shall upload this video to the LMS as well. And by the way, people, බලන්න අර quiz එක හදාගන්න පුළුවන්ද කියලා. Submit කරන්න මේ answers, okay? If it doesn't work, then just drop me a message saying it doesn't work. I'll see what I can do. Lecture note එකත් එතනම තියෙනවා, so you can look at the lecture note as well and then refer the video again. And if you have any questions, you can ask me. You can just drop me a message. Yeah, so until I see you again on next Monday at the same time, take care and be safe. Yeah, so that is it. Shall I end it now? Did you understand the lecture? I shall upload it again so you can, I shall upload the video so you can go through the video again while looking at the lecture note.